So today I will present a multi-scale modeling framework for composite materials, focusing on how our product suite enables efficient simulation workflows. I will briefly introduce the motivation, then focus on the core capabilities of our products in this domain, and finally illustrate a process with a concept case study. So we know that composites are widely used in various industries, from automotive and motorsports to aerospace, consumer electronics, and many other industries. So they are used mainly due to their unmatched strength-to-weight ratio and design flexibility, but their heterogeneous nature and anisotropic behaviors induces complexity. They are used in variable forms, from short fiber, continuous fiber, reinforced plastics, in layered structures and layups as woven fabrics, and in many other forms. So we know that their behavior is governed by interactions across different length scales. In order to capture their behavior, we need to have a multi-scale approach. So the multi-scale modeling tries to bridge different length scales and tries to resolve localized phenomena so that we can capture the material behavior and use simplified models in material models in upper scales that at the same time capture the phenomena in the global structural response. So, for example, here we see the micro scale of an FR4 woven layer that is used in a PCB. So we can go deep in the micro scale, see the interactions between the fiber and matrix, then understand how the woven fabric behaves, and then go to upper scales with homogeneous layers, and finally the whole model. So apart from composites, we can use this multi-scale approach for other materials as well that are actually heterogeneous, like a battery. Here's an example of a battery cell. So if we see in the nanoscale, we can see that the cathode is a porous material, and then we have the jelly roll which has both the anode, the cathode, the separators, and then the whole layer stack that creates the battery cell, and finally the battery pack. And a more, let's say, traditional structural application where we have composite components and we can investigate the interactions, go to the layered structure, and then move on to subcomponent level and the whole assembly. So if we take a look in our product suite, and especially ANSA preprocessor, PLC's FEA solver, and Meta post-processor, from this multi-scale modeling aspect, we can find tools that give us the capability to look in both micro and macro scale. So starting from the ANSA preprocessor, There are tools for the virtual material characterization for both mean field homogenization and FE homogenization methods. And at the macro scale, there are dedicated tools that allow the user to build laminated cell and solid models, and of course set up analysis for all major structural solvers. At the post-processing, Meta can be used for automated FE homogenization of the microstructure based on the results of all supported solvers. And at the macro scale, there are dedicated tools that enable the access and visualization of layered results and, of course, post-processing capabilities. In between, you can see a PLYSYS FEA solver, which can be used both for analyzing and solving RV models in the micro scale, and of course laminated models at the macro scale. So let's have a closer look in these tools, starting from the mean field homogenization tool. So this tool inside ANSA estimates effective composite properties using semi-analytical micromechanics. These calculations are done based on the constituent properties, volume fractions, and the shape and orientation of the fibers inside the matrix. The tool supports both linear and non-linear models, and the purpose inside ANSA is to generate the material card, the material model that will be used in further macrostructural analysis. The tool will create the material cards for all supported solvers, structural solvers, and it is a useful tool in at the early stage design of the material, at the process of material design, due to the fact that it gives the result instantly. So these are semi-analytical micromechanics, so we have instant homogenized properties. Now, mean field homogenization is also available in the ANSA Results Mapper tool. ANSA Results Mapper was earlier today shown in a demonstration, but here we want to point out that users can perform the mapping of fiber orientation from manufacturing simulations onto structural models and directly compute localized orientation-dependent properties. This is crucial for capturing process-induced anisotropy, especially for short fiber reinforced components. And furthermore, an implementation of the mean field homogenization is also available through user material subroutines that are given as material libraries for Abaqus and LS-DYNA solvers. So that means that homogenized properties are computed dynamically during simulation with Abaqus or LS-DYNA based on the local fiber orientation and the composite's volume fractions and the evolving loads. So this approach provides a true multi-scale coupling and a live prediction of the stresses and strains at the composite, matrix, and fiber level. Moving on to another approach for estimating homogenized composite properties, we have the RV generator that can be used for FE homogenization. So the tool can create different types of microstructures from short fiber, unidirectional, woven, layered, or even lattice structures and foam structures as RVs. So the model will create this representative volume element that describes the material microstructure. It will generate the FE. It can apply periodic boundary conditions and give us a ready-to-run model for all structural solvers. So based on the results of this FEA analysis, Meta will access the results automatically and will perform homogenization based on the full field of stresses and strains. Finally, we will get the homogenized material card inside ANSA. So again, here the outcome is the material card for the structural solver that we will use further inside ANSA. Now, at the macro scale, ANSA offers a variety of tools that enable the creation of laminated models. With the redesign of version 25, some new tools were added, and maybe some of the existing ones are relocated. But definitely inside ANSA we have the capability to define layer sequences, modify orientations for both cell and solid composite models, inspect and have reporting about the lamination information, such as the ABD matrices, and of course we have the capability to convert cell models to more detailed solid models or even hybrid cell and solid laminated models. All these tools are available for all structural solvers and will give us DEC inputs for these for the supported solvers. Now, talking about solvers, ANSA enables the direct job submission. This functionality was showed earlier today in a demonstration as well. So ANSA enables direct job submission and live monitoring for all supported solvers. User can view solver logs in real time, and errors are highlighted and linked with specific model entities. So this allows the user to perform immediate troubleshooting. Moving on to post-processing, Meta streamlines the post-processing for composites by extracting and visualizing results per layer, generating through the thickness plots, calculating failure indices and failure envelopes, and of course, we can take advantage of the automated reporting and all the automation capabilities of Meta. Now, let's see briefly an example. Actually, this is a concept case study where we will combine some of the tools that were shown in order to analyze the wishbone of an F1 car. So the wishbone of an F1 car is created by two titanium alloy members and a carbon fiber member. Of course, we will focus on this carbon rod, and we will follow these steps. We will start from the mesoscale and we will perform the material characterization through RV analysis. So we will generate the RV, we will perform FE homogenization, and then use this material at the macro scale where we will perform a typical CAD translation, meshing, lamination buildup, abacus setup, and submission, and of course the handling of results. So starting with the material characterization. So the material that we have is carbon fiber. We will use woven fabric structure, and the matrix is an epoxy resin. So through the RV generator tool, we create a woven type microstructure, and through this interface we select the weave pattern, the custom weave pattern that we want. Here we used a twill 2x2 weave pattern. We set up the matrix and fiber properties, generate the RVE FE model, applied boundary condition, and solved with epilices for homogenization. So from the response of this analysis with epilices solver, we get the effective engineering properties by averaging full field stresses and strains. Finally, the result will be the orthotropic material properties, and for this woven material, and up to this point we are solver neutral. So we have the orthotropic properties for this material, and we select to generate out of this homogenized properties an Abaqus material card. So this material will be used as the layer material for the composite rod. Now, at the macro scale, we import the CAD model inside ANZA. We perform the meshing, so we use unstructured tetrahedral mesh for the titanium members, and we use structured hexahedral mesh for the composite rod. So it's quite a thick rod, so we use hexahedral elements. Now, for the lamination buildup, since we have hexahedral elements, we will use the fill solid functionality of ANZA, and in order to bring the lamination information. So there is a file containing the layer information, the thicknesses, angles, and materials, and this function will be used onto the existing hexahedral mesh, and will try to fill the solids with layers up to the point that their actual volume, their actual thickness is captured. Then the lamination will continue to the subsequent hexas. So we pass the information, the lamination information, and we respect the actual mesh and geometry at the same time. This will result into a zone model with layers covering different areas of our model. This solid laminate model can be handled through the laminate tool, where we can inspect and even modify layers. Up to this point, again, we are solver neutral, so this is a solid composite laminate that let's say, it's solver neutral. So at this point, through the laminate tool, we assign the Abaqus material that exists in our ANZA session from the previous homogenization procedure. The next step is to set up a simple Abaqus analysis. So we define some interactions between the composite rod and the titanium members. We apply some constraints and boundary conditions to simulate 4 different load cases. So the wishbone is fixed at this end, a ball joint is applied at the other end, and forces, 3 different forces are applied in different combinations to simulate different loadings. For the interaction definition, we use the automatic detection of contact regions of ANZA. So the contact areas are detected, and we assign a tie contact between the titanium member and the composite rod. Of course, any other type of modeling contacts can be used once the regions are detected. Then we specify the constraints and the boundary conditions to apply on our ends, and finally we define different forces applied on different steps, and of course the concentrated loads. So once the 4 different analyses are created, they are directly submitted to Abacus at the same time, if we have the licenses, at the same time through ANSA. So once they, so we have the job monitoring live inside ANSA, and once we are done, we proceed with the post process. So this is the result of the worst case scenario. So the challenge when in Meta we have also tools that allow us to inspect lamination information and also modify material limits if we want to evaluate failure criteria as a post-processing action. And the challenge is to access the all layered results. So when we are dealing with composites, we have multiple results per element and per layer. So with the redesign of version 25, we are also introduce a dedicated tool that allows an efficient approach in reading and accessing layered results. So user can select all the type of layered results that exist in the output database, stresses, strains per layer, or even failure indices or reserve factors or any other solution-dependent variable that can be calculated by the structural solver. And all these layered results are read massively, and we can also create templates to reread these results in another model. Once the results are read, we have the 3D plots inside Meta, and moreover, Meta allows the generation of through the thickness plots. So we can specify the type of results that we want to see through the thickness. So any type of layer result can be visualized as a through the thickness plot, and by selecting different areas of our model, Meta will give us the distribution of the variables through the thickness. So this functionality is available for both cell and solid models like we have here. So Meta will, when we select an area, a point, an element of our model, Meta will gather all the hexes through the thickness and get the layered information. So we have the distribution through the thickness even for this kind of solid modeling with different rows of hexes. Additionally, we can have failure envelope plots calculated by Meta for the selected layers. Now, as it was shown previously by Christos, all the actions, the post-processing actions and reporting capabilities of Meta are recorded as session files. So we can reapply the same actions, have the same kind of reporting for all the other load cases. And this concludes my presentation. So we have seen a framework supported by the comprehensive capabilities of ANSA, Meta, and Epilisis that provided a multi-scale approach for micro, meso, and micro-scale modeling. We saw an end-to-end workflow from RV generation to laminate model build-up and solver integration within the same unified environment of ANSA, and advanced post-processing for both FE homogenization and in-depth exploration of layered results through the thickness. Finally, all these tools and processes that we see are solver neutral and available for all major solvers. That makes our solutions adapted to various industries and applications for engineers and CA. So thank you.
Okay, thank you, Michaelis, for your interesting talk. So let's proceed to questions from the audience. Yeah.
Very nice talk, and I have two questions regarding the RV generation possibilities in ANSA. For example, when we are generating like a composite RV in ANSA, does it have a function to also place like a cohesive zone elements between like fiber matrix?
Yes, the tool can generate contact definitions between the matrix and the fiber that allow the user to simulate contact separation laws and simulate the interface between fiber and matrix.
That's super great. Second question, does ANSA also allow to like define multiple different RVEs at the different locations?
Yes, actually, each RVE is generated in the same ANSA session at a different model space. So we can have multiple RVs inside ANSA, and we can also have yes, the homogenized results from multiple RVs in the same ANSA session. Okay. And all this is also available through scripting. So multiple RVs can generate it with the Python API of ANSA, and homogenized results can be generated massively with Python.
Thank you very much.
Okay, yes.
Thank you. So I think with the RVEs you showed something where there was a woven material.
A woven, yeah.
Yeah, and then you showed some draping simulations. Is it possible to have like RVEs with different like shear angles for the material and then correlate that to the shear angle from your draping simulation so it uses the appropriate RVE?
Yes, these two things that you mentioned are in different scales. So we do an estimation of the draping result at layer level at the macro scale, so at the part, but for the RV, it's a planar woven fabric. Now, I don't know if, yes, I can imagine that you can generate the planar RV and maybe use morphing capabilities of ANSA in order to modify the shape once you have the RV model from the tool. But yes, this is an approach that requires morphing capabilities of ANSA.
Okay, so kind of if the fibers of a rope are not in a 90-degree angle, you would need to morph the RVE to kind of get a different angle.
Yes, that would require some pre-processing manual effort.
Okay.
But I think it could be done.
Hi, thank you for the presentation. Is it possible that we have different stacking sequences for different elements, for, let's say, a variable stiffness composite where we can control the fiber steering?
You mean
Let's say the fibers are changing
yes.
along the different layers directionally.
Yes, yes. So yes, through the laminate tool of ANSA, you can have one property for your part and define different layers at different orientation and covering different areas of your part. So you have this flexibility, and you can also have custom orientation per layer. So follow an edge, follow a feature of your model. So a layer can have custom orientation for its fibers.
Okay, thank you.
Okay, anybody else?
Vangelis, thank you for the presentation. If we would like to have a parametric definition for the RVA, for instance, create a gyroid, is it possible to do it in ANSA now?
Gyroid as a structure, as a microstructure, is not directly supported, but I mean, the tool is enhanced in every version, so this could be also something that can come in future. So yes, of course, if the user can generate the gyroid through ANSA scripting and geometry functionality, of course this can be used as an RV for the whole process afterwards. That's yes, the RV generator handles also RVs that are generated by external tools. So you can bring them in ANSA, mesh them, and then proceed with the homogenization procedure.
Okay, any other question?
I can try without it.
You can.
We want it to be recorded.
Well done, Vangelis. I would like to ask if non-linear properties can be estimated during the RVE analysis.
Okay, so yes, in the example that I showed, we estimated the elastic, linear elastic properties, but as I mentioned, the RV generator tool can generate ready-to-run models for all structural solvers. So once the model is generated with the boundary conditions and it's ready to run, user can apply material nonlinearity for the fiber, the matrix, or even the interface between the fiber and matrix, and then After the solution, the tool will give the nonlinear estimation of homogenized properties.